record. Very good. Okay, then today we will talk about multidimensional systems, starting with multidimensional maps. Of course, life isn't always one-dimensional. There are many dimensions to life and to the system that you might want to model. And these systems might vary from ecological systems, like I told you at the beginning, that might be numbers of animals of different species, and each species can be seen as a dimension in your parameter space, or the development of an epidemic, or of course, you have some physical models, but usually it's more fun to see these models because can be mapped in discrete time steps, even if they are not always discrete phenomena, but they are pretty good to map in discrete time steps because they're more, maybe it's just because they are more human. So it's something that has to do with ecosystems and humans. And so you kind of think of it as in a cycle way. So every day or every week or every year, they have their own pattern. And then you want to model, you might want to model not what happens in each single moment at variance with a physical system, where if you have a pendulum, okay, you can model it at each swing, and each you can divide it by periods, but at the end of the day, it's a very continuous phenomena, and there is no reason to prefer any special way of dividing how this phenomena evolves. So for these type of systems like penduli, yeah, and climate models and this kind of stuff, it's very used to make a continuous model that is represented by what is called a flow. And we will see this probably after the Easter break, because the problem is that people tend to confuse maps and flows, but they're two very different things. In maps, on the other hand, as we've seen for the one-dimensional map, time is discrete, it's not continuous, so it's not described by so flows are described by a system of differential equations that describe the time evolution of the system, and since they are differential equation, then the time evolution is continuous. And while maps are discrete, so they describe the time evolution in discrete steps, or any other type of evolution, and therefore is well suited to have to describe systems that have a natural cycle. So, for example, in the predator-prey model that we will see as first example, this wants to model the population of predator and prey in a given environment. So that you have a predator, you have a prey, or you have a parasite and you have a prey. So this is often also called as the parasite-prey model. So you have a parasite, and the parasite has its own life cycle, and the prey has also its own life cycle. So you can think of these life cycles as one unit of time, because many things can happen in between, but on average, the same things will happen. So for example, if you take year by year, you can have that your prey has specific times in the year where it reproduces. And you have a gestation period, or you can go to lethargy. You can have many different things that can happen to an animal over the year. And the year is the natural time unit for these systems, because over a year, many different things happen, but year by year, roughly the same things happen. If you're not describing a big mammal, which takes almost a whole year, or for some mammals more than 1 year to gestate, if you take a small mammal, or if you take other type of animals, they will have gone through different cycles of gestation and over the year. And these cycles of the gestation and reproduction And that's are usually average over a given year. So you will have that more animals die during the winter, then the animals gestate more during the spring and the summer. So you have these kind of cycles. And if you take a whole year, then all these point-like structures, you average them out. So if you want to just describe the trend, the yearly trend of an evolution of a population of prey and parasites, taking a year long is a reasonable assumption because these are natural time steps, and therefore you smooth out all the characteristics of a single time period. And in this way, you can very well describe the long-term evolution of these two populations. If they go to have a stable solution when you have a certain number of predators and prey, or parasites and prey, or if the parasite is going to drive the prey to extinction, for example. And this cannot be seen if you look at well, it can be seen if you look at given time period, but yearly basis gives us a natural time scale. So this is a very good way of modeling some phenomena. So these ecological niches are very well modeled in maps. Economics is often quite well modeled in maps. If you don't want to look at the fine details of the stock market day by day, then you might use some stochastic and stochastic differential equations. But if you want to have a long-term view of economics, so what happens to two competitors that battle for the same market, according to the properties of these competitors, it is exactly the same situation. You can have that they make some seasonal product, they make panettone for Christmas, and then during the Christmas period, these will be very different than the rest of the year for the two competitors. But on average, year by year, these two competitors will battle on the same pool of clients. And so you can see that if one produces more than the other, or if one prices itself more than the others, according to the response of the market, you can see if one competitor drives the other to bankruptcy or not. So you have these kind of models, and there are few projects in our course that relates to these, either to these multidimensional maps to describe either ecosystems or economics or other type of systems. So you have plenty of choices. And about that, you have to remind me to talk about projects before the Easter break, so that you can try to look for it and try to think of what would you like to do. Okay, so I hope this is a clear qualitative description of maps. I think we can go to break already, and then we make a stretch. So you can have your morning coffee and wake up before the, I give you the definition and then we go immediately to break, okay? Sorry for deceiving you, but it's a very simple definition, so you can think about this definition. So there's the screen mirroring thingy, okay? So from this qualitative point of view, we've seen that one-dimensional maps is something simple. So it's just the definition, the description of the status at a given time step, respect to the status of the previous time step. So this we've seen the logistic map before, or complex maps just before when we talked about fractals. And complex map kind of guides you into multidimensional map, because if you take a simple multidimensional map, it's exactly the same thing, but where these are all vectors. So you have many dimensions to your system, okay? So F here goes from R in R, And in this case, f goes from Rn to Rn. So, and this relates to the fractal because fractal are complex maps. And then you know that R to the R square is homomorphic to the complex plane. Okay? So, in other words, this is like x. So I will do, this is why I did the other notation. Now I see why my notes had the other notation. So I also define it and use it in this way, even though you have to take into account that this is not in function. This is not definitely the x of j plus 1 is not x of function. So we have two notation, both of which are not ideal, but yeah, I did not came up with a better notation to satisfy our system. Because now, as you can see in the multidimensional maps, you simply have many dimensions. So you have in the first dimension, this is equal to f at the first dimension, depending on x1 of j. So sorry, this is only j, of course. X2 of j, xn of j, and then x2 is the same thing, f2, and you go on until you arrive to the nth dimension. So yeah, let's write it like this, and then we go to break. Okay, good. So let's have a break, and then we will talk about an example of this. So let me stop the share. Okay. So welcome back. Of course, you should ask me questions if you don't understand. But apparently, it's too easy for you, so you're not asking questions. But that's okay. Okay, so let's continue in the description of the multidimensional maps, and this thingy here done. Okay, so I'm sharing my screen. So you see the definition of multidimensional map is pretty easy, and it's very easy to see that I can leave you as an exercise that basically if you take z of j plus 1 equal to z of j plus c z square of j plus c with let me pull up the chat and your things, even though you don't write on it much, but at least I can see if you raise your hand or do something. Okay, so it's very easy to see. If you take the quartic map, you can demonstrate very easily that this corresponds to the some kind of logistic map. This corresponds to a map in 2 dimensions, and it has very straightforward correspondence with the logistic map. Okay, by setting the real part of z equal to x1 and the imaginary part of z equal to x2. So you can expand it and see the correspondence with the logistic map explicitly now. Okay, now we can do the Nicholson Bailey model and start to see an example of these multidimensional maps. Nicholson Bailey, was it like this? I hope I'm not writing wrong the names, but okay. So this was developed in 35, so very long time ago, to describe parasite host dynamics. And then it was modified way more recently in the 70s to kind of describe in a better way this parasite host dynamics, or generalized to predator prey. And they've seen that in a closed environment, this model was pretty accurate in describing parasite and host dynamics. So let's see, originally, the original Nicholson Bailey model had made this map. So was describing in the first dimension, this is the population of the host. Let's write it a little bit more on the way. Okay. So x1 is the dimension of the host, and this is R, a given fecundity, reproduction rate for these animals. And then you have x1 at the step j, of course. And then you have to add the probability of not being infected. So e to the power of minus a, the number of hosts number of host one parasite can occupy, or the number of parasite and host can occupy, depending if a is greater or smaller than 1. And then you have x2, which is the population of the parasites. And x2 is the population of the parasite. Okay, so this is equal to the population of the host, because if you don't have any host, then all the parasite dies as well, times the probability of the parasite to occupy a host. 1 minus e, that is 1 minus the probability of a host to not be occupied by a parasite. X2 of j. Okay, so where R is the reproduction rate, e to the I don't remember if there is a plus or minus. I think minus a x2 j. We will check soon enough. Is the probability of not being infected. So I spared you the details of which type of parasite was this modeling, because it's pretty gruesome and it's early in the morning. But the idea is that in this case, a parasite will infect an host, and then over the course of a year, for example, of a time step, it will kill the host. So if your host is infected, it will not be alive the next year, and it will not reproduce for that year. So therefore, x1 times e to the minus a x2, if we put j here, this is the active population of x1, okay? Because if if it is infected, so if the probability of not being infected is 0.9, it means that 0.9, the population at the previous step will be able to reproduce, while 0.1 will die off because it's infected of the parasite. So therefore, this is a simple exponential model for the host. So the host can continue to reproduce at infinity, and it's only limited by the interaction with the parasite. And the parasite, on the other hand, can be alive as long as it has a host to infect. If it does not have any host, then the parasite cannot be alive. So the number of parasites at the given iteration will be the probability of a host to be infected. So it's 1 minus the probability of not being infected, of course, times the population of x1. So in our previous example, it's the probability of not being infected would be 0.9. It means that the probability of being infected is 0.1. So the number of parasites at the next iteration will be 0.1, the number of hosts, okay, at the same iteration. So that's pretty much the system that they modeled Nicholson Bailey, and they were in the 35, so pretty trailblazing work for 35 mathematics. But this was working for at the very beginning of this parasite host dynamic. And this was attributed to the fact that, of course, these works these equations do not take into account the effect of the environment. So if you have a perfect environment which is infinite amount of resources, then the host can continue to multiply exponentially. But we've seen in the first lecture that this is not the case for most realistic systems. It is only at the very beginning of the reproduction stage. And if you wait long enough, then the host will kind of occupy all available resources. And at that point, we will not have any more space to expand, and will either die off or asymptotically reach a given fixed value, as we've seen in the case of the one-dimensional map, of the logistic map. This was a pretty good description. You have this very complicated behavior. So this was not feasible in 35, precisely because there were not the computational tool of doing this. In 35, the computational tools were people. I mean, they were hiring people for doing this sort of calculations. You just hire somebody which done high school and just put him down and calculate and iterate one iteration after the other, but this does not get you very far compared to a computer. And you cannot study complicated patterns. So you need to have a very good reason to hire a person just to calculate. And of course, this can be a very good reason if you want to send a man to the moon or develop the atomic bomb. But probably studying parasite host dynamics with these esoteric mathematical constructs was not in the priority of the founders, of the founding bodies. So there were no budget for this type of project. But in 75, as we know, no computer came along, and then people started using computers to calculate instead, mechanical computer or electronic computers to calculate instead of human computers. That was what was used before. And this unlocked very many avenues of research and scientific inquiry, including this. So the sophistication, as you can imagine, the sophistication introduced in this Nicholson Bailey model to include the effect of the environment was to have a cap, a kind of cap that represents the capacity of the habitat. So instead of R, of the big R that is just the reproduction rate, in this case, in 75, they were not big on logistic maps, but instead of being R was substituted with an exponential term. It was R21 minus X1 divided by C, where C is the capacity of the environment. Okay, so when X1 starts to be close to 1, then this exponential goes to 1 and kind of stops the evolution. If this increases over 1, then this surpasses the capacity of the environment. Respect to the logistic way, the logistic map of mapping this is a little bit more leeway. It's not that if you surpass the capacity of environment, then you are basically screwed and doomed to extinction. The environment can accommodate a little bit more and then simply will correct it in the next iteration. And this may be a little bit more realistic way of modeling. And this was really, really successful in modeling parasite host dynamics in the environment that are controllable by humans. So in laboratory environment, where the environment is fairly small, it's not that you can have, in this case was a parasite of spiders, I think, if I remember correctly. So even if spiders are not chimpanzees and are pretty manageable in decent numbers, you still cannot have thousands or tens of thousands of spiders in a self-regulating environment cohabiting with parasites. So you will have a pretty contained experiment. So in this pretty contained experiment, the capacity of the environment is fairly limited. So if you don't model for the capacity of the environment in these laboratory conditions, you will never describe your experiment. On the other hand, if you try to do it in nature, where the environment is large, and it might be that nature can accommodate a very, very large number of spiders, and it's way larger than it is happening. So we can consider the environmental resources as infinite, but then the non-laboratory conditions are way more complicated. You cannot just limit yourself to the fact that the spiders are either die off due to the parasite, or they continue living indefinitely. This is definitely not realistic. So, and then you have ecological niches that get covered, and then you have other predators. So you will have a way more complicated model, which is feasible, which is done. And in one of the projects, if you look at the GitHub page of the course, there was a relation between this Nicholson Bailey model, parasite dynamics, and, for example, sex. This is also sexual reproduction. What I mean, this is also a way one can study this system. So if you introduce sexual reproduction, then you have not only species, one species for the host, one species for the parasite, but you have two dimensions for the host, which are male hosts and female hosts. And then you need them to combine to make up new children. And therefore, you add complexity to the system. And what this does, by adding a sexual reproduction into the description of this parasite host dynamics, is also modeling and mixing the phenotypes. So you can have a phenotype which is more affected by parasites, and a phenotype that is less affected by parasites, and by doing a sexual reproduction instead of this type of naive reproduction, and admitting the fact that the progeny will take some characters from the mother and some phenotypical characters from the mother and some other from the father. So you have these mixes of phenotypes, then it will be more or less affected by the parasites. And then you can see that the sexual reproduction kind of regulates the parasite, because we will see very soon that this system is fairly unstable and will kind of quite easily, not always, but fairly often drive the two species to extinction. So the parasite will drive the host to extinction, and the year after, also the parasite will be extinct because there are no more hosts. So X1 goes to 0, and X2 will go to 0 the next year by default. So if you add sexual reproduction, this makes it, and some type of modeling of the phenotypical evolution of parasites and hosts, this is a very good, it's a very simple model of what biologists call the Red Queen chase. So in Alice in Wonderland, you have the Red Queen that was running all the time, and it makes a good quote that was, in this place, you have to run to stay still, and you have to run twice as fast to go anywhere. So this is basically what happens in evolution. You have to continuously evolve to catch up with your competitors. But if you want to win your ecological niche, you want to dominate your niche, then you have to go even twice as fast. So the running is the default setting. If you don't evolve, if you don't make this mixture, this phenotypical mixture, and therefore account for, due to the fact that the parasite will kill those phenotypes that are not resistant to the parasite, if you account for these, then it means that the phenotypes must continuously evolve and build up resistance to the current waves of parasites. And the parasite has to continuously evolve also to attack this system of defense, which is sexual reproduction. And so you can see this in a very nice model. So you can go and have a look if you're interested in biology and this type of things. So, okay. Now let's continue to model. So I will not do a super step-by-step derivation because I think it's fairly boring. This is a fairly long algebraical system, but so the fixed points of this system are, of course, 0, 0. So X star, this is equal to 0, 0. So one of the fixed point is 0, 0. If you have 0, if you have 0 in X1, then you will have 0 in X2, and then you are in a fixed point. You will iterate 0, 0 forever. And that's the definition of a fixed point. But there is another fixed point. So I don't know how to denote that this is the one of the two fixed points that we have in this system. So I give you as an answer the fact that X1 is equal to R logarithm of R divided by R minus 1. So my notes are a little bit confused if this is big R or small r. I think this is big R. It is small r. So do you understand this character here? I've been scolded sometimes because my undercase R looks like a drunken 2, but I hope it's clear that this is an R. So X1, so the population of the host has this fixed point. Oops. So we can verify this. I will not derive it because it's a little bit boring. It has logarithm and stuff, but it's of course it's feasible to derive it, but we can check it just to have to be sure that we are dominating the set of equations. So this is host and this is parasite. Okay, so we can verify by substituting these numbers in our equations above. So let me see. So our equations above was like this. So I think this was big R. Ah, yeah, no, this was big R, not small r, I think. Sorry for the confusion. Let's verify. Let's verify, and then we will see. Okay, so this big R, x1 star e to the minus ax2 star. This is equal to, if we consider this r log r, r minus 1, then this is r squared log of r divided by r minus 1 a, and then e to the power of minus a, and the x2 is just log r divided by a. So a and a get simplified, and then you're left with r squared divided by e to the power of minus log r is 1 divided by r. So this is what you get. And then you have logarithm of r divided by r minus 1a. This gets simplified here, and then you obtain the fixed point above. So this was big R. Yeah. So I did it for the simple system. The situation where I substitute with the account for the capacity of the environment, it's a little bit longer, and it's way more boring to do it. Analytically, it's very difficult actually. So we have to do it numerically, and we will see now how to do it. Okay, so this is x1. So I verified that in x1 is a fixed point if I account for that x2 star. Let's do for x2. So x2 is simply x1 at the fixed point, of course, 1 minus e to the power of minus a x2 star. So this is equal to r log r divided by r minus 1a. Oops. And then if I substitute this, I will get exactly the same thing. So this is 1 minus 1 over r. Okay? Just like I did before. So this can be simplified. Yeah, okay. Let's write it explicitly. Log r divided by r minus 1a. And then this becomes r, and this is r minus 1. Okay? And then r minus 1 and r minus 1 simplifies, r and r simplifies, and I'm left with log r divided by a, which was exactly my definition of the fixed point. So you see that there is a correspondence between fixed points here, and the fixed points that are defined here. Okay? So these are fixed points for the original Nicholson Bailey models, for the traditional one of the 30s. Okay. So what happens now if I want to study the vicinity of a fixed point? Is this fixed point stable or not? What happens in the vicinity of a fixed point? So this is similar to the one-dimensional case. What I have to do is to study basically the derivative. But now we are in many dimensions, so we need a little bit of multidimensional calculus. So are you familiar with Jacobians and multidimensional calculus, finding minima and so on in multidimension? I think you have a fairly diverse set of experiences. So there are some of you which are a little bit more behind in the classes that are years before, but I think of you present here, there should be, all of you should be quite familiar with that. You are third years or above. Okay. So if you haven't done it, that's a shame. I try to contact each and every student saying this is kind of a requisite for the course and it is in the syllabus. But we will use only, of course, it in a very practical way. Now the neighbor is starting to sing again, and this is disturbing me a lot. But okay, so in a similar way to the one-dimensional case, we can consider the linearization, just like we did in the one-dimensional case. So behavior at fixed point. Okay, so similarly to the one-dimensional case, I want to study the delta of x of j plus 1. So I want to study if I take 2 points that are close to each other, one is at the fixed point, the other is a little bit more far away. What does it happen? So this was one-dimensional, and this was very easy. So this is xj, and this is delta x of j, where delta x is defined as x star minus x, okay? So I take 2 points where x star is the fixed point and the other is close to the fixed point. So you can generalize the same principle in many dimensions. So this is fairly easy to visualize. So you have to generalize this in many dimensions, and the way you should do it is by using the Jacobian. It is exactly the same thing as the derivative. So instead of calculating the derivative, you kind of calculate the Jacobian in many dimensions. So this is x of j, delta x of j. Okay, where so this is sorry, this is not the gradient, but it's the derivative respect to x. Okay, so this is called a Jacobian J, and is a matrix where I put all my derivatives, my partial derivatives of f. So f vector, it means that it has many dimensions, 1, 2, 3, 4, and so on and so forth. And also x vector has the same number of dimensions. So this Jacobian would be simply a square matrix where I have the derivative of f1 respect to x1, the derivative of f1 respect to x2, and so on and so forth, and the derivative of fn respect to xn, sorry, the derivative here of f1 respect to xn, and then I have the derivative of f2 respect to x1. Yes. So let's do it a little bit better. Dots, and then I have the derivative of fn respect to x1. My God, my calligraphy on this thing already is an ugly calligraphy, but I hope you can read it. So this is my Jacobian matrix. Okay, that is the derivative in many dimensions, if you want to simplify it in this way. So this is derivative of fn respect to xn. Okay, so I hope you are all familiar with the Jacobian, and then the Jacobian has to be evaluated in a given point. Okay, so and the point it's a given xj. So that in this case would be usually we used to do that we evaluated the fixed point. So that's what we used to do in one dimension because it was convenient to see the behavior around the fixed point. And therefore this is exactly the same. So should I, is it super clear or should I show you how does it work in 2 dimensions. I hope this generalization is good enough for if you are familiar with the multidimensional calculus on why this formula correspond to the Taylor expansions in time away. Okay, they soon goes away. So is it fine like this, or do you want a 2-dimensional example? It's clear enough for me. Clear, okay. So if you don't speak, you get pounded, but who speaks? Okay. So let's keep it general like this. I think you can follow it. And if you want to do it, just do the 2-dimensional example to kind of as an exercise, and this will make you understand a little bit better. Okay, now what we can do with these derivatives. The point is that now we live in a multidimensional space. If we consider 2 dimensions, that's pretty straightforward. We have 2 dimensions. So I prefer to spend the time like this. I have 2 dimensions. I have a map in 2 dimensions, and I have a fixed point here. And then I want to understand that if I consider another point, if I put my map, if I calculate my map at the fixed point, by definition it stays at the fixed point, but if I put it a little bit away from the fixed point, what does it happen? Will it go towards the fixed point or go away? And if it does go away, will it go away? There is an additional layer of complexity. In 1 dimension, we just either it approaches or it goes away from the fixed point. You have only 1 dimension. At most, you had the choice that it could approach it by alternating larger and smaller than x, than the fixed point. Here, you don't have a notion of order. You don't have a larger than x star or a smaller than x star. You can, at most, have a larger than the radius of x star. What you have is a little bit more complicated situation where this point slightly away from the fixed point can go away in several different directions or can approach from several different directions. You can approach it like this, for example. So it will approach it by doing it kind of like a spiral, because why not? Or it can go away like this directly, or it can go away in a specific direction or tend to a specific direction this way. So many things can happen. And we want to study not only if the point is repelled or not. If we want to study if the point is repelled or not, we just calculate the Jacobian, we calculate the determinant. I forgot to put absolute values here. I put it on one side, but not in the other. So we calculate the determinant, and that's it. Then we find out if it goes towards or away from the fixed point. But we can know more. We have the possibility of knowing the direction in which this goes. So does anyone has any idea how can we find out the direction? In the meantime, I write it down. The red point can approach nobody dares to write how can you do it? How can you find out the direction of approaching or repulsion? Repelled by the fixed point over a direction. Nobody. How do we find out? So nobody dares to say the magic word. The magic word is eigenvalues. We compute the eigenvalue of the Jacobian. If the eigenvalue of the Jacobian will tell us, and the eigenvalue will tell us if it is repelled or attracted over a given direction, and the corresponding eigenvector will give us the direction. Okay? And why is that? Because this is exactly the property of eigenvalue and an eigenvector. The eigenvalues are finding the eigenvalue of the Jacobian find the preferred direction. The eigenvalue of any matrix, what do? Is diagonalize over a new basis. They find out a new basis and then they diagonalize. In the case of the Jacobian, what this means is that you find the basis where the map has its most characteristic behavior. So you find the two directions in which your, in this case, that is two-dimensional, you will find two eigenvalues, two eigenvectors, and this the eigenvector will correspond to finding the two directions in which these will have the most characteristic behavior, and the eigenvalue will be correspond if it gets attracted or repelled over one of the two directions, and how much, okay? So this is exactly what it means to have eigenvalues, to find out a new basis. And I also hope that this is clear, and if it's not, we can pass a little bit more time. You should ask me. If it's not clear, you should ask me, either this time or next time, even better. You think over it during the vacations, and then you ask me next time. Please, first thing, next time you will ask, please explain me eigenvalues and eigenvector, and how do they relate to directions. There are very good videos on the internet, very good resources on the internet that can show you visually, but you kind of have to understand it algebraically to kind of make sense of it. Okay, so we have to compute eigenvalues and eigenvector. And if you remember your algebra, since nobody said anything, I don't know if you don't have it clear, but since nobody's complaining right now, it's kind of like you have it super clear. So I don't know which of the two, if you're timid and you know everything, or you don't know anything, or a linear combination of these, speaking about eigenvalues. So the eigenvalues and eigenvector will be the vector and the corresponding value by which this is satisfied. So if you apply your Jacobian to a given vector, you will get back the same vector times a factor. And therefore, this is why it's a given convenient basis which preserves the direction, the properties of your map, and kind of enables you to study in the most characteristic way possible. And so if you do write this over this basis of eigenvalues and eigenvector, how do you do it? It's you calculate to find out. This is a bit reminder. You should have it more or less clear, but you simply do this. You calculate the determinant of the Jacobian matrix minus the eigenvalues over the diagonal. So this is fairly simple. And then you will you will find out eigenvalues and eigenvector. And then you can express your delta x vector of j plus 1 on the basis of these eigenvalues and of these eigenvectors. So you can express this on the basis of eigenvectors, and you sum the eigenvector over some xi, okay, on this new basis. So not on the previous Cartesian, for example, coordinate, but on the new basis. So for example, you have this Cartesian coordinate. This will give you x and y, let's say. But then you calculate your, I know that I use x1, x2. I hope you are flexible enough to kind of accommodate this misuse of notation, but right now I don't have any better idea. So you have this Cartesian notation, and you can represent your delta x in the Cartesian notation. So this is, we can zoom in, and basically this is your delta x. But this can be, if you calculate eigenvectors of the Jacobian, you will find out how these maps behave around a fixed point. So this is what you're finding. And you will find out two eigenvectors like this, why not? X1 and X2. And these will correspond to the two eigenvalues. Therefore, this vector delta, this is the vector delta x, can be expressed in these other bases of x1 and x2. And in these other bases, then you will have some factors, and you will have to multiply by the eigenvalues to find out the scale that is reproduced over these new bases. And therefore, so this is equal to sum over I of lambda I, and then you have some epsilon, which is just a small number. This is the usual small number notation for epsilon. And then you have some vector, so this is delta, some vector over your basis. So this is the eigenvalues. So as you can see, this is simply a this notation will indicate that this is simply expansion over all the possible eigenvalues and eigenvectors. So this gives us whether a fixed point is stable or not in the same way that we did in one-dimensional systems. So let me check if I'm forgetting anything. Okay, I always arrive a little bit with a little bit of time, with not much time to explain this part. And I'm a little bit afraid that you will not understand it, but luckily you can go back in YouTube. So please try to grasp this before we come to the next lecture. Okay, but so we have this notation. I hope it's clear. If it's not, write a question or stop me right now. And this gives us a basis in which we can find out what happens. And what happens is these eigenvalues. So if the eigenvalues is greater or smaller than 1, this will say what happens in the to the phase diagram in the direction of the eigenvector. Okay, so in 1D, we had that f prime of xj of xj was greater or smaller than 1, and then this will give us if it was stable or not. So if the absolute value of the derivative was lesser than 1, then the one-dimensional map was stable. If it was greater than 1, the one-dimensional map was not stable. So the fixed point was repelling. So if you started very close to the fixed point, you will get away. And then the sign will tell you if you go to plus or minus, and that's basically it. But if in this case, then we have one for each of the eigenvector directions. So in ND, we have a lambda I, and each lambda will be greater or smaller than 1. And this will again indicate if something is stable or not in a specific direction, in a specific direction corresponding to the eigenvector. So, for example, this is an indicator that you can have different type of things. So, for example, let's draw a couple of examples here. So, this fixed point, and then you have eigenvector in this case like this, and then you have 1 and 2. And let's suppose that lambda 1 is greater than 1 and lambda 2 is smaller than 1. What happens here is that the phase diagram, this is called the phase diagram. I don't know if it was clear. Probably I cut it a little bit, but I hope it's clear. So this represents your map in the same way that in one dimension, the phase diagram of one dimension was represented by the map. So this diagram here will tell you the evolution. It's called phase diagram, and will tell you the evolution of the system over the two directions. So if you take direction 1, for example, and lambda 1 is greater than 1, it means that over this direction, this will tend to be repelled over this direction because lambda 1 is greater than 1. While over this other direction, lambda 2 is less than 1. I forgot the absolute value. And this can go on in an alternative pattern or very straight. That doesn't matter, but what it matters, let's not add too much complexity, is that this goes in like this. So this is called a saddle point. Just like in multidimensional calculus, you see saddle point because they are the minimum in one direction and the maximum in another direction. This does the same. So what happens if you put a point here on this direction, this will go straight to the fixed point. I use this rainbow thingy. If you put a point here, close to the fixed point, but in the other direction, this will try to go away and will drive off to infinity. So if you put it in a point in between, like here, what happens is not super clear. In this case, it will probably go away like this. So we'll follow the trajectory and we'll try to get closer and closer to the eigenvector trajectory. If you put it here, for example, we'll tend to get closer and closer to the fixed point in this direction. Okay, and then you will have trajectories defined in this way. I hope you can see the rainbows, fantastic rainbow. Okay, so this is called a saddle point. One other thing that can happen is a source point. So this will go if you can get lambda, which belongs to the complex number. So instead of being a real number, it's complex. And in this case, then for 2 dimensions, it will be related, the 2 lambdas, lambda 1 and 2, will be given by the same absolute value, and then e to the plus or minus. One is plus, the other is minus, e to the theta, to the given angle. So they will have the same angle, but will opposite, at opposite angle with the same absolute value. So this is a property, due to the property of the Jacobian, then the eigenvalue can be complex, but the only way they can be complex is that if they are complex conjugate. So this is because of symmetry properties of the Jacobian. And so these indicate a spiraling structure. And this can be either a source, so when it goes inside, or a repel source when the modulus of lambda is greater than 1, or can be repelling when modulus of lambda is greater than 1. So smaller than 1, of course, the source. So it can be either be attracted to the fixed point, or the fixed point can repulse. And okay, So lecture is basically finished, but I wanted to go over the Lyapunov exponent, because then we finish up with maps, and I don't want to confuse the maps. So is it a problem if I go forward 10 minutes? Does somebody has to go away? So let me, okay. So you have this kind of phenomenology, and I'm doing it a little bit rushing, but there is not much theory that you can extract from this. It's just something that either is one way or is another way. What you really need to do to prepare for the exam is to do exercises and find out for a given map what happens. What are the fixed points, if they are source, if they are depending, on which direction. So try to do the exercises and ask Alex at the exercise section about all of these and examples, and try to really understand this, because this is something that you have to develop a sense for. And so, for example, if we do it for the Nicholson Bailey model, in the Nicholson Bailey model, the Jacobian, you have only two dimensions. Therefore, the Jacobian is given by the function, the derivative of the first and the derivative of the first dimension with respect to the first, and the second dimension with respect to the second, and so on and so forth. Okay, f2x1, f2x2. So I have no time to make you go over it, but it's pretty easy to do derivatives, of course, with respect to one or the other factor. So you can kind of immediately see that is something like this: 1 minus e to the minus ax2, x1 minus a e to the minus ax2. So you simply derivate the factors. And if you substitute this in 0, so you calculate this for 0, 0, what you obtain is the only term that does not directly depend. So this goes to R, the first goes to R. This goes to 0 because x1 is 0. This goes to 0 because x2 is 0, so the exponential is 1. And, sorry that I cannot say this. So this one is, the first one is R, because this goes to, the exponential goes to 1, and you're left with 1. This goes to 0 because x1 is 0. This goes to 0 because the exponential goes to 1, and you have a 1 minus 1. And this goes to 0 because x1 goes to 0. Okay? So therefore, the Jacobian is done like this. So it's pretty simple in 0. And what this implies is that you have two directions. In this case, it's already diagonalized. So the eigenvalues and the eigenvectors are already diagonal. So the eigenvalues are the natural x1, x2, are the parasite and host direction. And sorry, the eigenvectors are x1, x2. And eigenvalues are R and 0. So this very, the old-fashioned Nicholson Bailey model, what happens is you can represent the phase space like this, where you put x1, x2, and then what happens is that for x1, the eigenvalues is r, which is positive because it's the reproduction rate of the host, so it repels over x1. x2 over x2, the eigenvalue is 0, so exactly as for one-dimensional maps, it means that it's super stable. Okay, so it goes very quickly to 0. 0, 0 is a fixed point. Then you have another fixed point on the other side. And I leave you as an exercise, if you want, to find out that the eigenvalues in this case are complex. And what does this generate is these dynamics that is repelling. So the behavior of the Nicholson Bailey model is that the traditional Nicholson Bailey model is that the population of parasite and host will spiral, and according to the reproduction rate will spiral more or less fast, but you will have one year with more parasite and less host, the other year with even more host and less parasite, the other year with way more parasite and smaller hosts, and the other year with even more hosts, and so on and so forth. You will alternate here with plenty of hosts, with way more and more hosts, and years with more and more parasites, until you arrive to a breaking point where you reach extinction, either of the parasite. If you hit here, then you reach the extinction of the parasite and the host will live happily ever after, or according to the parameter of your space, how the reproductive rate of the host and the infectiousness, the parameter A of the parasite will go, you can hit it here and this will immediately go. So the parasite will extinct the host. So these are the only two things that can happen in the traditional Nicholson Bailey. But if you include the environment in this, then this regulates the behavior and kind of smooth this behavior out. Okay, so it already passed 7 minutes. Now, another thing that is very similar to the one-dimensional maps is the Lyapunov exponent. Lyapunov exponent, okay? And the problem with this, with the Lyapunov exponent, is that the eigendirection changes with each iteration. So there is no fixed f prime. There is no fixed derivative at the fixed point that can tell you and tell you about this exponential behavior that grows or not. What you have to do will be again to look at the eigenvalues. So there is no direction, but you have to look at the eigenvalue. And so the delta x of a given n iteration, where the delta x is the fixed point and some point very close to the fixed point, for example, this is proportional to delta x of 0. But now, since you have several directions, this will go in very different way according to which direction. Just look at here. If you start from this case, you will go exponentially on growing in one direction. And if you go in this other way, you will go exponentially stable in the other direction. So two different directions will have completely different behavior, and this behavior will be given by the eigenvalues. And the eigenvalues really show this exponential behavior. So this is lambda I n, where n is the number of steps in your Lyapunov exponent for a given direction, vi. And this can change of the direction. So you can, depending on the Lyapunov exponent, this can be greater than 1 or equal to 1. So you can have cases where lambda 1 is greater than 1, so you have a positive Lyapunov exponent in one direction and lambda 2 that is different than lambda 1. This is fairly, fairly common. Sometimes lambda 2 is greater than 0. So it is smaller than 0, sorry. So very, very often, if your map is non-trivial, what you will obtain is always that you will have one direction that is greater than 1 and other directions that are either smaller than 1 or smaller than 0. So you can order what one usually do when solving a system is order the eigenvalues in from the greater to the smallest. So you order it by number, and in this way you can see if there are many eigenvalues with positive sign and greater than 1, that indicate this is going away from the fixed point or not. And so this is a little bit more complicated than the one-dimensional case, as you can see, and especially the study of the Lyapunov exponent is way more complicated, not having a preferential direction, and the positive Lyapunov exponent will not always tell you the chaotic nature of the system. So in one dimensional, we've seen that in one dimension, if you have a positive Lyapunov exponent and a non-periodic behavior, then it means that your system is chaotic. Here you can very easily have a positive Lyapunov exponent in one direction, another Lyapunov exponent that is lesser than 1 in the other direction, and have a perfectly well-defined behavior which is non-chaotic. So the Lyapunov exponent is less indicative in complex cases than it is in the very simple case. Okay, so I think with this I conclude the lecture. So let's continue the recording for the people that are not here. So an important announcement for all of you is the project. So there is a list of projects on the website, on the canvas. So let me share my desktop. Let's do the desktop. Okay, now you can see my desktop. You can see my browser. I hope you can see me going in Canvas. Can you? Can you see me going in Canvas? Yes, very good. So I go in Canvas. I have many courses, not only yours. And then we have this, the home page is this. You will see different pages for different sides of the class. So this is fine. But you have previous exams that you can kind of look and kind of see what you have, some extra material. What we have is also projects. Okay, I will add here a list of projects. It's not right now, and what you can do is on the, oh, well, I cannot find it, but so I will show you from my own directory. I will put this or something very similar to this online that has a list of projects. You can find it in the old website, but I will modify it slightly. So chaos. And then bear with me a second. Ah, is it here? No. Okay. Matfis FMFN05. So this is the old, and then you have a list of topics. It will be a file like this one, if it loads or not. So you have a series of projects, but what I want you to do is either choose one of the projects from the list below. If you are master students, you are encouraged, let's say, I encourage you to suggest your own project. So there are several things you can do. You can find in the GitLab page. So if you go to GitHub, sorry, and then there is an organization called Lund in Chaos. You have previous project that you can download and look at. This is what I was telling you, the Nicholson Bailey project. And usually it's taken from some article and you kind of try to reproduce the results that they had in an article in one way or another, or do something fun with it. So this was a very nice study of the parasite host behavior that I was telling you. So now you have sexual reproduction of hosts, and you have different species of hosts and different species of parasites. And as you can see, you have this very complicated dynamics. And if you introduce more and more phenotypical mixing, you kind of stabilize the population of the host and of the parasite. So this is kind of the results, and it's a nice thing. And you have your code that generates everything related to the project. So this was proposed by the students there, Helen Ellen and Eric, I think. Oh yeah. Sorry, I don't remember your name, but you were a very good student. So I remember your surname. So now, master students are strongly encouraged to suggest their own project. It can be fun, but you can always take a list. PhD student, I think Bjorn is the only PhD student, but I'm not sure, are expected that you choose your own project so that we can work on something, even maybe a fairly bit original. That would be top. And there is a list of projects, so you can do several things. Now you have seen multidimensional maps. What you are missing is flows. So the system of differential equations and how to recognize chaos in multidimensional system. But basically, there are several examples. So crystal growth, for example, or parasite host dynamics, solve models of propagation of fire. This is used, another tool that is called cellular automata. And then you have kicked rotor system, for example. This is a very popular example of chaotic system. So some coupled oscillator where you kick one with a given frequency and you see the effect on the other. And then you can have chaos on a pool table. So if you have your usual rectangular pool table, then it's not chaotic at all. And it's, you can predict the trajectories. And if you modify slightly the trajectory, then you will modify slightly also the outcome of your shot. So this is why we can play pool. But as soon as you put obstacle in between, so if you put some fixed obstacle or other balls in between, or you make the table not square, but some other shape, which is not regular, then you can have a chaotic game of pool, which will be maybe, I don't know if more or less fun, because it would be more chaos, but less skilled dependence. And then, so you have these kind of things. You have the formation of cloud is a self-organizing system, which is very, very fun to study. You have market behavior, as I told you, both with maps and with flows. And you have weather chaotic behavior. So this is all interesting projects. Here it says with Gunnar, but of course it's not Gunnar, but it's me. You have to sign up with me. And you have the Easter to think of possible projects. And so basically that's it, I think. The project will be worth 1.5 credits, and it's only pass or fail. So the vote will be given by your exam, and the project will be only pass or fail. But I think it's a fun part of the course, and I don't want to make it too standard or too I mean, to be affected too much by this pretty unusual situation. So let me stop the sharing of the screen so you can see me. So I don't want to make it affected too much by this unusual situation, because it's really an added value of the course, that you can kind of interact with a researcher. That would be me, can be Alex. Alex will be given a couple of projects as well, given by his own research topics. Can be Sven, maybe, will like to. He's a very experienced researcher that did a lot of studies in quantum chaos. So, and was the course responsible for me. So it's an opportunity for you to interact with the researcher and to kind of see the world from a different perspective, in a sense. I mean, you can go out in the world, find out behavior which is you find non-trivial, and then we can kind of find a way to model, search the literature, the usual stuff, kind of do some work on how a researcher experienced in modeling would behave, and kind of you can have your shot at playing to be researcher. Okay, so don't waste it. And happy Easter, and we will see each other, I think, the 28th. So in more than 2 weeks' time. So yeah, there will be 2 weeks of break. We will see the 28th morning. There will be a lecture, and in the afternoon you will have exercise with Alex. So do you have questions regarding the projects or regarding the topic that we've seen? I know that it's very late. I'm very sorry about this. I needed to finish fractals and to do this topic so that you can go over it over the Easter.
I wonder when we should sign up for the projects.
So you should try to sign up, in my opinion. So you can either sign up next time. You can also wait for 1st of May. That starts to be a little bit late. But on the other hand, in this way, you will be able to see flows. And you will be able to see, okay, I prefer the treatment of maps, or I prefer the treatment of differential equation, or I prefer to do something different. So you can have a preference. I'm afraid that if I force you to choose right now, then all of you will go either with maps or with fractal, with stuff that we see and you are more familiar with. So kind of think of a system, think of a possible topic that you will like to have fun with, and then we can think of a method. You can think of a method after we've seen flows, and you should try to. So 28 there will be lecture, 29 will be lecture, and then there will be Valborg. That will be also very strange this year, and then we will see each other on Wednesday 6th. So I think by Wednesday 6th of May, you should really have a project pinned down. If possible before, if you are really sure that you want to do something with maps, then all the better, and if possible before. But last date would be 6th of May. I will write it on the website. So last date for subscribing to a project, to sign up for a project, would be 6th of May. Okay? And then the project takes 1.5 weeks. So, sorry, it takes roughly 1 week of full-time work. So a couple of weeks of half-time. You have other courses, really depends also on your load. The idea is to have it done by when you do the exam. So in a month. So that I think is feasible. It really depends on your load in courses. It can be feasible in a week, or it can be feasible in a month. It's fine even if you do it, if you deliver it later. It's just that I disencourage you to do it because you tend to be forgetful. You say, yeah, and then it's very easy that the summer comes and then you don't think about it anymore, and then you let it go until fall, and then you forgot what you done in the course, you forgot what you studied, you forgot what you wanted to do, and yeah, then it gets too much. Should you work in groups? Excellent question. So yes, you should find out a group. I understand that there is a little bit extra difficulty, but if you don't find a group, then let me know. I mean, you should try to find a group. If you have a friend, contact them and try to think together. Groups of 2, 3 people, 4 people is ideal. 3, 4 people, I think, is ideal. It's a little bit crowded, but if you do use GitHub, 3 or 4 people works. If you don't want to use Git, then do it less. And I will discuss I will come at the exercise session next time, and I will discuss more organizational point of view, like what you should do. But the size of the class of your group will also depend on the tools that you want to use. If you don't want to use Git, then it's 2 people. And if you don't find anyone, just drop me an email about the project that you would like to tackle, and then I will try to find a fit for you. So try to find somebody. Since the situation is like this, if you don't find anyone, and since you cannot talk in class and you cannot see each other's faces, you cannot find who you already know or whatever you've seen around, you think is a good guy and you want to do the project with him or her. And yeah, I will try to group you by topical preference if you don't find anyone. Other questions? Okay, so let me stop the record.